Okay, so welcome back. Now we have a nice, I would say, E in, which looks mathematically convenient. And now our goal is to kind of minimize this because that's what we want, right? In any problem that we're looking at, we really want to minimize the in sample error. Okay, so first of all, does this E in make sense? Well, it does because it's mathematically convenient and we can do a lot of things with it as we'll see going forward. The other thing is how to find the W's, so basically how to find these weights that will minimize my E in, right? That's the goal. Just by looking at the E in itself, you can see that let's say if my yn, the observed value is -1, right? Then in order to minimize or like in order to make this E in really, really small, I would require this term, right, to be less than 0 and as less than 0 as is possible. Similarly, if my yn equals +1, then I need this W transpose xn to be greater than 0, right? So that I can get a smaller E in out of W. This is kind of an intuition that we are getting out of like how can we minimize, what things we need to do in order to minimize E in. Well, let's think about the classification problem that we looked at some time back, right? So when we were doing classification, in that case, we used the pocket algorithm or the PLA, the improved PLA was the pocket algorithm. And so we improved at every iteration, right? So we used the pocket algorithm and improved at every iteration. And then in the regression problem, we used the pseudo inverse algorithm, which was just like a one-step thing that eventually led us to the gradient of E in for the weights to be exactly equal to 0. Now, with functions like these, which are twice differentiable, for example, the E in that we have, we can use something that's known as gradient descent. So how does that work? So basically what we can do is we can calculate the gradient of this because the function looks convenient, right? But we cannot do it analytically. So we will have to do it iteratively. We cannot do it the way we did here in the pseudo inverse algorithm. For this function, that's not possible, right? So analytically not possible, but iteratively, I would say yes, possible. Okay, so what does that mean? So in order to understand that, let's look at this ball falling phenomena, and of course we are familiar with this. So like think of this as like a depiction of or a representation of some hilly area that has these valleys and then these mountain or like hilly terrain basically, right? And if you roll down a ball like from this top point or this point or this point, it usually ends up in one of these valleys, right? And one of like each of these valleys here is known as a local minimum. Why? Because like you can have like many minimums. You cannot see the entire hilly terrain, and then wherever it reaches, that's the valley that you've reached, and that's the local minimum here, right? So the question arises: how do we get to the bottom of the deepest valley, which in this case is this one, right? If I just roll down a ball here, it will definitely end up here and not here. But this is the deepest valley. This is the one that is like having the most depth, right? So how do we do this, especially when we don't have gravity, right? And so even in this case, like even with gravity and everything, if I roll the ball here, it is definitely going to end up here, right? So this is exactly what we are trying to achieve. Now, if you think of these valleys as nothing but the elevation being equal to like E in, I really want that, like I really want to reach at this point and not like end up here or end up here, right? That is going to be not good for my problem because that's not the actual global minimum. That's not the deepest valley. So how do we do that? Well, it's obviously not as straightforward as we think of this, but there is some good news about the E in. And then here comes in the idea of why we've been talking about this mathematically convenient function so much. So let's look at it. So here is the good news about our in-sample error. The in-sample error E in that we derived, it looks like something like this. So this is a convex function. And if you've taken optimization classes or other math classes, you know convexity is good news in, like, if you're trying to find the gradient, because now this is differentiable, right? So our in-sample error surface looks like this. What we have to do is just roll a ball and let it roll. Why? Because it will end up, because there is just one valley, right? And so basically we just have to find the weights corresponding to this point, and that is going to be the minimum error in this case. So that's good news for our E in, and that's why we were so much after that E in, right? Okay, so having said that, now we need a methodology to go downhill, and also some explanation of like where to begin and where to end and how to move forward, right? Because like in a real world, obviously you have gravity, you have friction, all of that that's working to get the ball rolling, but we have to make our ball rolling somehow. And how do we do that? Okay, so let us begin doing that. Okay, so what we do is like obviously if you look at it, look at this, we are interested in like getting the lowest weights. So obviously we'll begin with some initial weights, and then we'll iterate and move in a certain direction, and then iterate means like keep taking certain steps, right? So it's like with this I'll reach here and then take another step and reach here and so on, right? So let's formalize this approach and write it down here. How do we roll down, right? So how do we roll down? Okay, so let's say at iteration t, which is like my first step would be t equals 0, right? So at some iteration t, basically, I will have my weight vector at t, right? And at that iteration, I will pick a direction, right? So how do I pick a direction? Well, I pick a direction that is a unit vector, and let's denote that unit vector by v hat, and then take a small step in that direction. So take a small, I'm coming to what a small step means, step in that direction. Okay, so what does a small step means? Well, you can take, this is your choice, you can take a small step size and you have to decide how small the step is going to be, but let's denote that small step by eta, right? So this is my step size. Take small steps, be extremely cautious, keep taking these steps and keep updating your weights, right, until you reach a certain point. So basically we need to pick this v hat or my unit vector to make such that, right, to make my E in at wt plus 1, which is the next iteration, as small as possible, right? That is why I'm moving in that direction. We're coming to that direction because it has to be the steepest direction then, right? Because think about this, like although we are like viewing it in a two-dimensional space, if this was a three-dimensional space, there could be like multiple ways of moving towards like this valley, right? And so we have to pick the steepest one, right? So that's what we're trying to say here, so that this is as small as possible. So basically my iteration step wt plus 1 is denoted by the weights at wt plus eta times my unit vector. Well, how do we ensure that this is like the steepest direction, and what is the steepest direction? Well, the steepest direction is where the decrease in my E in is the most, right? So the change in my E in, and change is my delta, this triangle, do not confuse it with the gradient because we're going to use that as well. So this triangle is the change, right? So for example, let's say initially it is like E in at the iteration, the tth iteration, and then at the t plus 1th iteration, it's going to be wt plus 1, right? So basically the change is going to be the E W T plus 1 minus the, sorry, E in, right, E in W T, correct? And then we can use the first order Taylor approximation to expand this term, because this term first of all will be replaced by Wt plus eta times V hat, right? And because this is equal to this, right? And then we can use Taylor expansion to get the significant terms. And I'm quickly jumping to the significant terms only. And so what we're going to get is that this change in my E in is given by an yeah. So it's going to be the gradient of E in at t times eta V hat, because there is going to be an extra term that is going to be E in Wt in this one as well, in the expansion of this term as well, and both of them will get cancelled. So this is the most significant term that we're going to get. So this is the change, right? And so what exactly are we interested in? We are really interested in, so that the change in E in is almost equal to this, and by something that's known as Cauchy-Schwarz, I don't know if I'm spelling it correctly, inequality, right? This here is greater than or equal to the negative of this, like whatever constant we have, times the gradient, the norm of the gradient E in at Wt. Okay, so why is this important here? Well, what we want to do essentially is that we want a unit vector, this V hat, to move, like, if let's say this is my, let me show you, let's say this is the gradient of E in. So I really, to have the steepest direction, I want to move in the negative direction of that. So my V hat, I have to choose a V hat such that is in the exact opposite direction of my gradient of E in. Then only this is going to make sense. And by using this inequality here, this and this, both of these terms, this term and this term, they become equal when, and let me write it here, they're going to become equal when exactly, like the equality is attained rather, when this V hat is equal to minus the gradient of E in at the weights at iteration t over the norm of the gradient at E in. And you can see that, right? That's the only thing that gets sort of cancelled out. Okay, so this is like the best direction, and this is the negative of the gradient of E in. So this is the exact V hat that we should choose, because we said we have to choose this. So it doesn't come from like somewhere outside. This is the best direction. The best direction is to move in the negative of the gradient. And this is that direction. Okay. So once we have that, we are ready to summarize all of this. Like, what exactly is this gradient descent? Let me summarize it here. Okay, so the first thing that we do is initialize t equals 0, basically begin from anywhere. Well, there are lots of rules around this as well, where to begin. Usually you can begin at 0. If you have certain domain knowledge, take those weights and then move further and so on. So there are lots of like accompanying knowledge of where to get started. So that's a big question in itself and has been answered, of course. And so let's say at the tth iteration, my weight is t. What I need to do is I need to compute the gradient first. So compute the gradient like at these weights. So that's why this Wt, right? And then do the update rule in this case, which was t plus 1 equals Wt minus, because the negative sign comes from here, eta times, if you remember, the V hat, right? So V hat now is nothing but this delta or gradient of E in Wt over the norm of E in Wt. Okay, and then at t plus 1, like the next one, just keep repeating this, right? So we are finding the steepest direction and moving in that direction. And this entire process is known as normalized gradient descent, right? So essentially what we're doing is we are finding the steepest direction, as I said, taking small steps or steps of size eta. We are going to talk about like step size as well. And then moving in towards the negative of the gradient as fast as we could. And then this goes on until we achieve E in, which is really, really small. Again, there is a whole lot of literature around when to stop. And then just like the pocket algorithm, we can either decide the like maybe come up with a threshold of E in of where to stop. Or sometimes we really, really come down to a small E in and we see that there isn't a lot of change, and so we just stop. And this is how like the stopping criteria is decided. Now, another big question that still remains is how to choose like a reasonable eta or a reasonable step size. So we are going to discuss that in the next video.